Hello, everyone, and welcome to this session, which is about how we from Ericsson are using Istio and 5G Core cloud-native network functions. My name is Ingo Meirick, and I'm currently working as a cloud-native architect for Ericsson. I'm mainly looking into the connectivity and networking area for cloud-native applications, and service mesh is one of the main topics I'm dealing with. And today with me is my colleague, Faseela Kundattil. So Faseela, over to you, if you could introduce yourself.
Hello, everyone. Hope you guys are having an amazing time at IstioCon 2022, where we are enjoying great sessions from Istio contributors and users across the globe, describing how various complex use cases and deployments are realized using Istio Service Mesh. I'm Faseela. I work as a cloud-native software developer at Ericsson, where we power our 5G solutions with Istio. I work together with Ingo, and my primary responsibility includes representing Ericsson's requirements in the Istio community, contributing to the community with new additional features that are important to us, and at the same time collaborating with other community members to leverage other relevant functionalities that they are developing as well. Over to you, Ingo.
Thanks, Faseela. Then let's get started. A quick recap of the agenda for our talk today. So I will start with an introduction to the 5G system architecture and explaining what a cloud-native network function is about. Then continue with why using service mesh in a 5G core cloud network, a cloud-native network function. After that, I will explain what is specific to using service mesh in a CNF and what are the related requirements. Faseela will then take over and explain more technical details on how we make use of service mesh in a CNF. And we will conclude the presentation with what's next, where we are listing topics we are interested in and on which we would like to do further follow-up within the community. So 5G system architecture. It's shown in this picture on the right side, and I will not go into the details of all the boxes and what they mean, but focus on the architecture itself and explain the main concepts of it. So first of all, there's a separate control and user plane in this architecture. So the control plane is highlighted here by the light blue box. And the control plane is responsible for managing the data plane, like registration of devices, also called user equipment, establishing a data connection, and also maintaining the data connection. Then there's a data plane, which is highlighted by this yellow box. And the data plane is taking care of forwarding data from the devices to the radio network and then through the user plane function to the data network like the internet. So then there are the network functions you see here in the different boxes, which are defined by the 3GPP standard, the third generation project standard, partnership project standard. And for more details, you can also have a link later on to this reference and check the standard out yourself. It's a big document. And these network functions are processing functions in the network which have defined functional behavior and also 3GPP defined interfaces, which are shown by these circles here at the network functions. A network function itself consists of smaller unit functions, which are called network function services. So they are inside the network functions. And these are like microservices in a cloud-native environment. So that means that the 5G architecture is really designed for cloud-native, and network functions being implemented using the cloud-native design principles are called cloud-native network functions, in short CNFs. So the different network functions in the control plane connect to each other via the so-called service-based interface, SBI. This is an HTTP2 API-based interface and standardized by 3GPP, which makes it also possible that the network functions can be implemented by different vendors and interwork with each other. So now the question, where do we use and where do we want to put as a service mesh in this architecture? So the service mesh is most useful for some of the control plane network functions. This is because these network functions are using HTTP2 based protocol, which is supported by the service mesh. And also the control plane network functions have less strict requirements on the latency compared to the data plane functions like the UPF. An exception are the access and mobility function and the session management function, since they are also using non-HTTP2 based interfaces and are also in the critical latency path. So for these network functions, the service mesh is not so well suited. So why should we use Istio in the 5G core network? And there are these three main areas which service mesh is handling for cloud native applications and so also for cloud native based network functions. First area is security. So this supports encryption for internal and also external communication. It provides authentication and authorization of workloads and automatic certificate provisioning and rotation. Another area is traffic management, where we have layer 7 based load balancing and traffic steering for HTTP traffic. We have a handling of ingress and egress traffic and the support for network resilience and robustness. And last but not least, the observability area, which provides metrics, traces, and logging. So this makes the service behavior visible and also shows how services are interacting with each other. Here I'm showing how service mesh or where service mesh is located in the cloud native telco stack. So on the right picture, you see the cloud native telco stack, and in the bottom, there's a Kubernetes platform running on some hardware. Above that is the CNF, which is running the business logic of the network function itself, and typically has also some generic platform services, for example, for logging, metrics, and similar. And on top of that, for the lifecycle management, we have the management and orchestration layer, which is also defined by some telecom standards. So these CNFs are now operated by a communication service provider on a container as a service, or short CaaS platform, which is based on Kubernetes. The CNF and the Kubernetes platform could be from different vendors, and also multiple CNFs might run on the same Kubernetes cluster. So the question is now, where should we put the service mesh in this stack? And the answer is that we decided to include the service mesh into the CNF itself. So we do this to avoid dependency on a service mesh to be present in the Kubernetes platform. We don't know on which Kubernetes platform our CNFs get deployed. We don't know if this Kubernetes platform supports a service mesh at all. And if it comes with a service mesh, we also don't know what service mesh implementation it might be. And different service mesh implementations have different features, different ways to configure. So it would mean a big integration effort if the Kubernetes would be, if the service mesh would be provided by the Kubernetes platform. And that is something we want to avoid. Also, the split of the responsibilities for handling the service mesh, so that the service mesh itself located in Kubernetes, but the configuration in the CNF. So that's why we decided to put the service mesh in the CNF itself. That means that we have some additional requirements on an Istio service mesh included in the CNF. The first one is the support for multi-tenancy, since the service mesh is part of CNF and even multiple CNFs might run on the same Kubernetes cluster. We also identified the need for communication with services running without a sidecar. For example, services using non-HTTP based protocols, which didn't work well with Istio. So that is also an important use case for us, and Faseela later on will go into more details for this. Then we need to support specific 3GPP requirements for robustness and resilience. Here we use mainly the features from Istio Service Mesh to achieve this. For the lifecycle management, which is handled by the management and orchestration layer, we have also some requirements. First of all, the lifecycle management of the CNF and the service mesh are coupled since it's one entity. So this needs to be considered, for example, for installation and upgrading, and things need to be done in the right order there when doing this. Also, we have the requirement to support upgrade windows even greater than 6 months. So Istio is supporting 6 months upgrade window. We need to make sure that we support even longer upgrade window, and we do that also by using the Istio Canary upgrade feature. And last but not least, we need the support of Helm for the management and orchestration layer. Then some of our customers require support for dual stack, so that is also something we have implemented. And we adapt the sidecar resources according to the CNF dimensioning needs. And finally, we need to make sure to do the hardening and vulnerability testing. Some of these requirements will be discussed later on in more details in the technical part by Faseela. So let's look inside the CNF using Istio Service Mesh and check where we use which service mesh features. So first of all, the CNF is represented here by this box, and it includes the Istio control plane and the data plane components, like an ingress gateway, potentially also an egress gateway, and of course the sidecars attached to the network function services. The traffic is then, and also to mention is that we have some services which don't run with a sidecar, and also these ones need to communicate to services with a sidecar. Traffic is coming into the CNF from a consumer network function via the service-based interface, and then going into the ingress gateway. For traffic leaving the CNF, it's also going via SPI interface towards a producer network function. So let's start with the different service mesh features, and let's start with the ingress. So what does the ingress do for us? First of all, it provides termination of external TLS and MTLS traffic. So here we are not using Istio internal certificates, but external certificates. It supports hitless rotation of these certificates and optionally also validation of user identities. Also important is the overload handling feature of Envoy that we are making use of, and load balancing feature, which we use in the ingress gateway. And the traffic is routed based on the URI to the corresponding network function services. For simplicity, only 2 network function services are shown here, but of course there are multiple network function services within the CNF. We have also the ingress use case here at the bottom for traffic from a mesh external service going into an Envoy sidecar. So if this service does not have the sidecar and cannot use Istio certificates, we still want to have a secure connection here, and we use an external certificate for that. And this use case is something that will also be later on discussed by Faseela in more detail. Then the next one is the egress. So for the egress, we need to support origination of external TLS and MTLS traffic. Also here, we are not using Istio internal certificates, but the external certificates. And we need to support hitless rotation of the certificates. And the egress gateway and provide some enhanced security as it's a specific entity for leaving the traffic from the mesh. It could be run on a dedicated node, for example, but it's optional. We also, for some use cases, we don't use an egress gateway and go directly from a sidecar to a producer network function. And similar, within the CNF, we might have network function services talking to mesh external services. And here we have also this egress use case using external certificate, but originating from the Envoy sidecar directly, not using the egress gateway. And then on top, we have the three areas I mentioned before for traffic management, security, and observability. And we basically make use everywhere, make use of these features. So for the traffic management, for example, we use layer 7 load balancing. We use the layer 7 traffic steering, specifically at the ingress gateway. We provide resilience by using timeout and retries from Istio service mesh. And for the robustness, we are configuring connection pooling, circuit breaker, and similar. For security, we make use of Istio MTLS, which is coming out of the box, which is based on SPIFFE certificates, and we use it for all the mesh internal communication. It also provides authentication and authorization of the workloads and automatic certificate provisioning and rotation. And last but not least, we have the observability, where we have Prometheus metrics and use distributed traces and logging to make the communication in the mesh visible. This slide is just showing again the service mesh features in detail that I listed before. It's just for completeness. So for people who are looking later on the slides, that they get an overview about all the different features. And this includes the first part of the talk, and Faseela will continue now digging into more technical details.
Hi everyone. Now that we have got a clear and crisp idea of how a 5G system architecture looks like and the need for service mesh in the 5G core network, let us dig deeper into a little bit of technical details on the different usages or adaptations that were done to Istio based on some of our requirements. Let us get started with the traffic management related use cases, especially for ingress or egress traffic management, for TLS traffic handling, for mesh external services within a CNF. As Ingo already pointed out, it's not always possible to onboard all microservices within a CNF to the service mesh due to different reasons, be it lack of protocol support or performance reasons or complexity in integration. So there are definitely cases where there are needs for services within the cluster but outside the mesh to communicate to mesh internal services. This was one of the important use cases for us, and let us see how this was handled for the egress traffic. For this use case, it does not make sense for the traffic to go via an egress gateway, and it is very well desired that we are able to avoid this additional hop. Currently, Istio already has a mechanism to realize this use case, but it requires a very complex configuration. We can use a destination rule by specifying the TLS key or cert paths and later mount these certificates explicitly using sidecar annotations for volume mounts as shown in this slide here. And to add to this overhead, destination rule used to get applied to all the workloads, and this used to result in a lot of warnings or errors in the workloads so where these certificates are actually not present. To improve this situation, we have proposed certain enhancements in the community in this area already. And most of the work has been completed for the upcoming Istio release. One of the major highlights being the addition of workload selector support for destination rule. With this, it becomes easier to configure egress TLS settings for specific workloads instead of applying the destination rule globally. This solves the initial problem of the client certificate settings going to all the sidecars. On top of this, the ability to configure credential names via DR was added to the sidecar, which again simplifies things and makes it easier to use Kubernetes secrets for TLS settings instead of the need for specifying all these certificates and key paths in DR and then mounting them explicitly. The links to the RFCs and the PRs have been included in this slide so that it helps if any one of you want to refer to them in the future. A similar situation is present for the ingress traffic as well, where we prefer to avoid this additional ingress gateway hop. So far, this was achieved using a complex envoy filter to add a new filter chain for inbound traffic, which could do the TLS termination before forwarding the traffic to the workload. However, with the new experimental feature that has been added to the Istio 1.13 release by some of my colleagues from Intuit, the Sidecar API has been enhanced to support TLS termination. This feature called Enable TLS on Sidecar Ingress. It will be really useful as this avoids the overhead of using envoy filter for the use case. As you know, directly using envoy filters are always complex and requires a lot of care and consideration for lifecycle management. Multi-tenancy support is one of the major requirements of our 5G core solution, as there will be cases where multiple CNFs can be onboarded on the same platform, and it becomes crucial to isolate them in an appropriate fashion. There has been some bottlenecks for us to use vanilla Istio for multi-tenancy, some of them being Istio injecting sidecars to all pods and all namespaces. Not all Istio configuration is restricted to specific namespaces. Patching all validating or mutating webhooks, or monitoring or overwriting root CA config map in every namespace, etc. Some of these problems needed some enhancements to the code, while some others just needed only careful scoping of the various configurations that are allowed. So specific namespace labels were added to identify each tenant, and this was used to restrict webhook patching. We majorly used Istio discovery selectors so that create to change events for namespaces and config maps from non-matching namespaces won't result in unnecessary configuration. Also, configuration leakages for items like service registry, gateways, service entry, destination rule, and other CRs were carefully avoided. So for this, CRs uses export to and other scoping mechanisms. Gateway uses the pilot scope gateway to namespace feature flag, and service registry uses the discovery selector for careful config scoping. We are planning to propose an RFC describing this solution to get an early feedback from the community, and if possible, would like to contribute the additional changes which we had to do internally to realize multi-tenancy. Dual stack support is another crucial feature for 5G CNFs. We do have a downstream only solution for the dual stack support at the moment, which satisfies our immediate needs. And this solution uses Envoy's IPv4 compat mode. When binding to an IPv6 address, this mode enables IPv4 compatibility. The solution also overrides Envoy's local IP address version command line option with v6, and also takes care of setting up IP6 tables in workloads with Sidecar. While we tried to upstream the solution some time back, it was not considered suitable for all the combinations of use cases Istio community was supporting, especially the multi-mesh and multi-cluster use cases, and hence the solution was not really accepted. But currently, we are really looking forward to the new dual stack solution that has been proposed by Aspen Mesh and Intel, and the evaluation for the same is in progress. While we have certain concerns regarding the size of Envoy configuration this new solution is going to add, we are actively looking for options to give early feedbacks and collaborate on the shortcomings. We also use some envoy filters for enhanced use cases, which are not currently supported by Istio. Envoy filter provides a mechanism to customize the envoy configuration generated by Istio pilot. We use envoy filters to modify values for certain fields, specific filters, or even add entirely new listeners, clusters, etc. For example, in our case, to configure the ingress gateway to use a global rate limit server, we configure envoy filter to identify global rate limit server IP address, port, and protocol. Another use case is for configuring the filter, HTTP tap filter, to tap requests on the sidecar. Another envoy filter is also applied that enables TLS 1.3 for access to the upstream services. Envoy filters usually must be used with care, as incorrect configurations could potentially destabilize the entire mesh. So definitely we would prefer if there are support through native Istio APIs for all these above cases. So, what are the plans ahead? As already mentioned, discussing and collaborating for better multi-tenancy support would be one of the prime priorities for us. Better 12 stack support, we are hoping to leverage the new solution that is under development in the upcoming releases. Istio has the ability to process application level protocols such as HTTP, gRPC, etc. But as Ingo already mentioned, but for non-HTTP based protocols, better support needs to be in place. For example, to support Postgres, we needed to support Start TLS. So you need a network filter understanding the Postgres protocol. There will be several similar other use cases where we need support for non-HTTP based protocols. Um, we have seen advances around hierarchy, which provides a framework to allow Istio to support more layer 7 protocols other than HTTP. We are yet to explore the same to see if it meets our requirements. We would also like to explore the various new advancements in the area of proxyless service mesh, which talks about using gRPC, also eBPF, to enhance the performance of Istio service mesh. Another topic of interest to us is the integration to external CAs. I think we already had some nice sessions from solo.io yesterday at IstioCon around the same area, and we are looking forward to explore those options further. Another requirement is the need for best effort graceful termination of envoy during node failure or shutdown. There are also other 3GPP requirements as well that are evolving, which demands better certificate revocation support related to CRL, OCSP, etc. So we would like to continue to support the Istio community in achieving all these future use cases in terms of requirements, discussions, brainstorming, as well as code contribution and testing. Let us collaborate and work towards making Istio the default service mesh for all 5G core solutions. With this, we would like to conclude our talk and give some time for answering any of the questions that you would have. Thank you.